Hi everyone, thank you all for joining us. Tonight my team will be presenting our capstone project called the Eskay Creek Mine Design. Here are the 4 members of our capstone team known as DJMM Consulting. We would also like to give special shoutouts to our faculty advisor, Dr. Doug Milne, and our client, Roland Tosney. Eskay Creek is a historical underground gold mine in northern BC that opened in 1994 and was the world's highest grade gold mine while it was in production. It was closed in 2008 due to the low price of gold and lack of infrastructure in northern BC. The price of gold has climbed since, and there has been a significant amount of development in the area, making leftover reserves economical. Given a mine life of 13.6 years, our team has been commissioned to design an open pit mine, as well as give our recommendations for potential underground workings.
The area around the site is characterized by large ridges trending northeast with valleys in between. Temperatures can range from -40 to +30 degrees Celsius, and snowfall can be up to 17 meters annually. The picture on the left shows what remains of the site camp. However, most of the surface infrastructure is not considered usable and will need to be rebuilt.
The Eskay Creek ore body is a VMS deposit which is situated on a northward plunging anticline. There are 3 geological units of concern at the mine site. From the top down, they are the andesite, the mudstone, and the rhyolite. The ore is found within the mudstone layers and the rhyolite. For the design, we split the deposit into what we call the main ore body to the north and the 22 zone to the south.
Different types of geotechnical data was collected for this project, including RQD data, old workings ground support data, RMR data, and joint orientation information. As you can see from the photo, a lot of the rock we analyzed had poor structure and was very crumbly. Our team was also provided with drill hole data from a drilling program completed at the site towards the end of last year. We were able to import the data into a modeling program called Leapfrog in order to get a visual representation of the holes with respect to the ore body.
2 of the major controls on slope stability of the open pit are regional faults and weak layers of mudstone which intersect our pit walls. In areas where fault planes intersect the pit walls while angled into the pit, fault planes and associated sets of discontinuities can form blocks which may topple into the pit. The figure on the right illustrates the toppling failure mode. Also, the layers of mudstone, which will be present in our pit walls, are much weaker than the andesite and rhyolite and are prone to displacement and failure. In order to reduce these risks, our design alternatives include the use of wire mesh to prevent toppling and reduce slope angles within the mudstone to maintain slope stability.
After analyzing the geology and geotechnical data, we created 3 unique mine alternatives for our design. Promin was used in the design as it allowed for the calculation of ore tonnage and pit volume after creating rough pits with the use of cross sections. The first alternative is a large open pit which encompasses the entire main ore body. The second and third alternative are a combination of open pit and underground mining. They use the same open pit design but have different underground mining techniques. We use Olynyk Creek as a natural buffer for the pit extent. Alternative 2 uses longitudinal stoping as a primary underground mine method, whereas Alternative 3 uses transverse stoping. Since the 22 zone ore body is separated from the main ore body, we considered it as its own separate design. We split the 22 zone into 3 further zones, with zones 1 and 2 near surface and zones 3 being deeper. We found that zones 1 and 2 can be taken as their own open pit, and that mine out zone 3 drops the ore grade to uneconomical levels and therefore it will not be mined out in our design.
After evaluating the 3 alternatives, our recommended design is a combination of alternatives 2 and 3. This includes a small pit for the 22 zone, a larger pit for the main ore body, and deeper underground workings. In order to maintain a mine life of 13.6 years, the open pit operation will excavate about 54,000 tons per day. The recommended equipment consists of a fleet of 10 400-ton haul trucks, 2 electric rope shovels, and 1 hydraulic shovel. The recommended underground mining method is a combination of transverse and longitudinal sublevel stoping. The method used in each specific area of the mine will depend on the variable width of the ore body and the quality of the ground when mining begins underground. Ultimately, the recommended alternative was found to be the safest and most economic method possible. We would like to thank everyone for listening to our presentation today. Please visit our breakout room if you'd like to ask us any questions.